Hey there, and welcome. Today, we're going to talk about something you see literally every second of every day. Light. But, you know what? It's got this totally wild secret. A secret so huge it basically broke classical physics and kicked off the whole quantum revolution. So, let's dive in and uncover what's really going on with light.
So for hundreds of years, everybody thought they had light figured out. It was a wave, right? Simple. Just picture a ripple spreading out in a pond, smooth, continuous. That was the idea. And honestly, this wave theory was a superstar. It explained rainbows, how telescopes work, you name it. It was perfect, until it wasn't. Because a new mystery popped up that this beautiful wave theory just couldn't handle at all.
Okay, and this is where the story gets really weird. So scientists shine a light on a piece of metal. According to the wave idea, that light should kind of gently soak the metal with energy. And eventually, after a while, an electron would get enough juice to pop off. Makes sense, right? Well, that is not what happened. Not even close. Electrons were zapped out instantly. But here's the kicker. It only worked if the light was the right color, like a high-energy blue or violet. Red light, no matter how bright, did absolutely nothing. It was like light was acting less like a wave and more like a stream of tiny bullets. And for physicists at the time, this was a huge problem.
So what do you do with a puzzle that breaks physics? Well, you need a game-changing idea. And in 1905, that idea came from a guy you might have heard of, a young patent clerk named Albert Einstein.
Einstein's proposal was totally out there. He basically said, what if light isn't a wave at all when it hits something? What if light is these little packets of energy? He suggested each packet has a specific chunk of energy and momentum, which, are the classic signs of a particle. It was a mind-blowing idea, a true, quantum leap. And this new particle of light, we now call it the photon.
All right, let's get to know this photon. Think of this as its stat sheet. First up, it's a quantum of light. It moves at c, the universe's absolute speed limit. And here's a weird one. It has zero rest mass. What does that mean? It means a photon can't stop, ever. If it did, poof, it would just vanish. And the really cool part is that its energy and its momentum, its particle properties, are tied directly to its wave properties. We can even calculate them with these handy formulas right here.
Okay, so this brings up something that trips a lot of people up. What is brightness, or intensity, really? It's easy to think that brighter light means stronger photons, but nope, that's not it at all. Let me give you an analogy. Imagine a bright red light. That's high-intensity, low-frequency. It's like being pelted with 1,000,000 ping-pong balls. There's a lot of them, but each one is pretty weak. Now imagine a dim violet light. That's low-intensity, high-frequency. That's like getting hit with just a few rifle bullets. Not as many projectiles, but each one packs a serious punch.
So, here it is. The single most important thing to remember from all this. Write this down. A photon's energy, its punch, comes from its frequency. Period. Intensity, that just tells you how many photons are showing up to the party. That is the golden rule. Another thing about our photon's profile, it's electrically neutral. See, if you shoot an electron through an electric field, it's going to curve because of its negative charge. But a photon? It just sails right on through in a perfectly straight line. It's completely invisible to electric and magnetic fields because it has zero charge.
So what about when photons smash into things? Well, think of it like a game of cosmic billiards. The total energy and momentum of everything involved before the collision has to equal the total energy and momentum after. Those rules are ironclad. But, and this is a big but, the number of photons can change. A photon can get absorbed and just vanish. Or in other interactions, new photons can be created out of nowhere. It's a very flexible system.
All right, enough theory. That's the what. Now let's get to the how. How does this stuff actually work in the real world? Let's crunch some numbers and see what these photons are really made of. Let's start with a regular laser pointer. To figure out the energy of one single photon from this laser, we use Einstein's amazing little formula. Energy equals Planck's constant times frequency, or E equals h nu. Planck's constant, h, is just a fundamental number of the universe, so we plug that in, we plug in the frequency of our laser's light, and voila, we get the energy. And look at that number. It's tiny, like unbelievably tiny. Just under 4 times 10 to the power of negative 19 joules. That's a decimal point with 18 zeros after it.
So wait a minute. If one photon is so ridiculously weak, how can a laser pointer even make a spot on the wall? It's all about teamwork. It's the sheer number of them. We take the laser's total power, what it says on the box, and we divide it by the energy of just one of those photons we just calculated. And the number you get is Well, it's insane. It's 5 times 1,000 trillion photons pouring out of that little laser every single second. Mind-boggling, right? Okay, let's circle back to that mystery from the beginning, the photoelectric effect. Remember how we needed to knock an electron out of a piece of metal? Well, picture that electron sitting at the bottom of a little energy well. To get it out, a photon has to come in with enough of a kick to boot it right over the top of the well. That minimum energy, that height of the well, has a name. It's called the work function. For a metal like cesium, that energy barrier is 2.14 electron volts. And don't let the name scare you. An electron volt is just a super tiny unit of energy that's way easier to use when we're talking about single particles.
So, knowing this work function, we can now calculate the exact minimum frequency a photon needs to have to do the job. We just work our formula backwards. We do a quick conversion from electron volts back to joules, and boom, we get our answer. 5.16 times 10 to the 14 hertz. And this right here, this solves the whole mystery. Any light with a frequency lower than that, like red light, no matter how bright you make it, it just won't work. The individual photons, the bullets, just aren't powerful enough.
Okay, we've been through a lot of theory and some pretty wild calculations. So let's step back and put it all together. Here's the final verdict on the photon, and the toolkit you'll need. And this wasn't just some crazy idea that everyone immediately believed. It took time and proof. Einstein won the Nobel Prize for it in 1921. But then other scientists like Millikan and Compton ran these brilliant experiments that just piled on the evidence. By 1924, with Compton's work, it was undeniable. The photon was real. So let's recap the essentials. Rule 1, light acts like a particle when it hits stuff. Rule 2, the energy of that particle, the photon, is all about its frequency, not its brightness. Rule 3, while photons can come and go, total energy is always conserved. Those are the key rules to live by. And right here, this is your mathematical toolkit for working with them. And all of this leads us to the biggest, weirdest takeaway in all of quantum mechanics. It's like light is living a double life. As it's traveling through space, it acts like a big, spread-out wave. But the instant it hits something, boom, it's a tiny, single, point-like particle. A wave one moment, a particle the next. So, where does that leave us? It means light isn't a wave, and it isn't a particle. It's both. At the same time. This idea, this wave-particle duality, is one of the pillars of quantum physics, and it leaves you with a pretty deep question to chew on, right? If something as fundamental as light can be two opposite things at once, what does that say about reality itself?